The next talk is a remote talk again. We have heard a talk before on ADCs and DACs by Thomas Mögel from Roth and Schwarz. And he also mentioned a company that's producing those devices. There's a company called Analog Devices. And there is a person in Analog Devices who is doing very fascinating things, and this person is Jon Kraft. Hello, welcome.
Oh, hello, yes, sorry I couldn't be there in person. It sounds like a great conference. Next year.
But nevertheless, I'm happy that you can join this way. And of course, you're quite the distance away across the Atlantic. Where exactly are you in the United States?
Yeah, so I'm in Colorado, right near the Rocky Mountains.
Oh, that's cool. Beautiful landscape there, isn't it?
Yeah.
Okay, great. So you've brought us a topic about the ADALM-PLUTO. And the ADALM-PLUTO is a very well-known device because it's very popular in academia, and it's also a basis for many interesting projects. And there have been some updates recently, and well, you are going to talk about those updates and those new experiments that are possible. Since you are a long distance away, and we have pre-recorded your contribution, and the video team has it. So I would like to ask the video team to play the pre-recorded video. Please go ahead.
Hello, everyone. My name is Jon Kraft. I'm a systems applications engineer at Analog Devices. I mostly focus on our radio and radar platforms, and this includes all kinds of products and platforms, things like fully digital beamforming radar, satellite communication modems, this phaser kit that maybe some of you have seen before. So I do like these kinds of things. But for all of this, I think my favorite platform is this little Pluto here, this little Pluto guy. Nearly everything I do, I could find its start in Pluto. I mean that if I'm building a radar, I could probably build a smaller scale version of that with just Pluto. Or if I'm doing beamforming, I could build a simple digital beamformer with Pluto. And actually, I'll show you an example of that today. So this little Pluto radio is just very flexible. It really is a great tool for exploration and understanding, and a great tool for prototyping. You might find that some of your designs might benefit from doing a small, kind of simplified prototype of your project first with Pluto. And the software that Analog Devices provides is consistent across all these platforms that I'm showing here. So what you do with Pluto will directly apply to Phaser, to MXFE, Apollo, pretty much all of our RF, radio, and radar products. We released Pluto way back in 2018, but it's been so popular that we continue to make improvements to it and expand its capabilities. So this presentation is really about some new things that you can now do with Pluto. I'm going to start with a feature we released a couple years ago, and that is how to unlock the second receive and transmit channel of your Pluto. And then I'll do an adaptive digital beamforming example using this second channel, just to give you a reference on how to access it via software and show you something cool you can do with it. Then a new feature we added just last year is the TDD engine. This allows you to synchronize your transmit and receive buffers. And this enables all kinds of cool things like radar or half duplex communication. Then I'll highlight, I guess, kind of an anti-feature of Pluto. So this is what some might call a bug or a mistake. And this is an issue with some Pluto ESD diodes, and it could be affecting your performance, but there's an easy way to test it and to fix it. And so I will show you that. And then finally, I'll show you how to do this thing called context port forwarding. This will allow you to access your Pluto over longer distances. Okay, but first, just what is Pluto? I hope everybody in the SDR community knows Pluto, but it doesn't hurt to go over it again. Pluto is an open source design using the AD9363 0IF transceiver chip from Analog Devices. And then you can do a frequency expansion hack on it to open up its frequency range. so that the frequency range is 70 megahertz to 6 gigahertz. And then that will give you a max bandwidth of 56 megahertz, though I pretty much always operate it below 30 or 40 megahertz. Now, by default, Pluto has one receive and one transmit channel, but you can add a second RX and a second TX channel if you open up the case and use these little U.FL to SMA cables. And here's what that second channel expansion looks like. So first you'll need to modify your Pluto just a little bit. You just open it up and add that second receive channel. And there's a video and a link over there how to do that step by step. And it even walks you through, that video even walks you through the Python installation and use. And it ends with a simple Python script that you can run to ensure you've set everything up correctly. So if you want to build the digital beamformer that we're going to do in this lab, please watch that video first and just be sure that you can run that Python script. If you're running into any trouble on any of this stuff, go to the link that's in the bottom right-hand corner of this slide. So that link is ez.analog.com/ADI education/university program. Post your question or issue there, and always include as many details, graphs, pictures as you possibly can. And when you post, an expert from Analog Devices, an expert on Pluto is going to respond and work with you to get this resolved. However, but I guess before posting anything, please read all the documentation. Avail yourselves to all of the videos and literature and wiki sites that we have on Pluto. Pluto is pretty robust, so if you're running into trouble, try repeating one of the setup guides first. But then if you truly are stuck, then go ahead and post on that forum. And here's what's inside Pluto. At the heart of Pluto is this AD9363 transceiver IC. This is part of the Catalina family of direct conversion transceivers. So these products mix the RF signal directly down to baseband. So that means there is no IF frequency. And direct conversion is generally the simplest and the lowest power way to do this RF stuff. And then inside of the chip, there's all kinds of continuous calibrations that are working to minimize LO leakage and quadrature imbalance. And the end result of this is really good. I mean, this actually makes for a really nice radio. Now, there's several ways to control Pluto. Pluto is easily controlled by MATLAB, and here are some links to get you started down that route. You can also control Pluto via Python. And for that, we use the PyADI IIO Python library. It's very easy to use. It has a lot of commonality across all of our RF and high-speed data converters. And you can also use Pluto with GNU Radio. And we have some Pluto source and sync blocks there that you can just directly connect up to your flow graph. But actually, what I prefer to do instead of using those blocks is just to do Python programming of Pluto from within GNU Radio. And you can do that with the Python blocks in GNU Radio Companion. But then, okay, then why not just do everything in Python? And really, there's two reasons that I show here. First, in GNU Radio Companion, it is very easy to integrate GUI inputs, graphs, buttons, etc. They all run smoothly. So that means I'm not wasting time building a GUI with tkinter or Qt. And the second is that the display updating is much, much faster than Python or MATLAB. It really is impressive how fast GNU Radio Companion can update a plot. And that's a big deal with a lot of the radar things that I like to do. And so here's what a GNU Radio flow graph with Pluto might look like for me, for how I might implement it. So I'm using the Python block, and then I just add my PyADI Python program into that block. So for installing Pluto with Python or Pluto with GNU Radio, I created this wiki site that has all my advice on how to do that. So you can go to wiki.analog.com/IIO install. So check that out if you need help getting started installing these programs and drivers. Okay, so let's do an example program using our 2-channel Pluto, and a fun example to do is adaptive digital beamforming. Okay, so what is antenna beamforming? Just real quick, antenna beamforming is you have some array of antenna elements and you're going to steer where that antenna is pointed based on a phase shift or time delay that you adjust between all the elements. So this allows you to steer the antenna beam without mechanically moving the antenna. And this is a very popular topic and there's lots of applications for this. What I'm showing here is an 8-element array where each antenna element is connected up to a data converter, and then the phase shifting or could be time delay, that's all done digitally. So some key terms in here first. X is the RF data from the antenna elements. So that means that X sub n is the signal received at element n. W sub n is the gain and delay applied to that element N. And then finally, Y is the output signal after applying all those beam weights to our received data. And when we do that beam formation, we end up with this sync style antenna pattern, and I've drawn it here over the face of the array. So you see the main lobe there, and that's where we've set our beam to be pointed. But then you see all these side lobes, and these side lobes are a problem. These side lobes mean that you may unintentionally pick up a jammer. And so there's several methods to deal with side lobes. They all have pros and cons, but the method I'd like to demonstrate here for our 2-channel Pluto is called adaptive beamforming. So the key with adaptive beamforming is we want to dynamically optimize our antenna patterns so that wherever there is an interferer or a noise source, that we will optimize the antenna pattern to give us a small antenna gain. And then wherever our desired signal is, we want to optimize to have a larger gain there. And we want to do this dynamically by first analyzing all the data that we receive and then calculating an optimal set of beam weights to form our antenna pattern. Okay, so how do we do that? How do we find that optimal set of beam weights? These equations are the mathematical way of saying exactly what I had just said. So we want to minimize the power. That's the W Hermitian RW term. But that minimization of power needs to be subject to keeping our beam pointed in the direction that we want. So this is a classic constrained optimization problem. And so solving this constrained optimization problem gives us a solution called MVDR, or minimum variance distortionless beamformer. This is sort of I guess maybe an entry level or somewhat foundational adaptive beamforming algorithm. And it gives us this great equation for computing the optimal beam weights, this WMVDR beam weight vector. So in this equation, S is the steering vector. That's the direction that we want to steer the antenna to. R is something called the spatial covariance matrix. And this is just calculated from the data that we receive on each of the antenna elements. And that is kind of a whole topic unto itself that I don't really want to get into right now. But let me say, before I go any further, I want to highlight that everything I'm presenting here on this adaptive digital beamforming is just a tiny snippet from a tutorial workshop that I put together with Dr. Marc Littman, Dr. Mike Piccolo, and soon-to-be Dr. Tarun Kusek. We did this presentation last year at the IEEE Radar Conference in Denver, and then again at the conference in Atlanta. And I think we'll be doing it again at the Radar Conference in Poland. So it was a hands-on workshop to explain the basics of adaptive beamforming. This adaptive beamforming has a sharp learning curve. It has some nutty math in it. And so the four of us set out to kind of try to demystify it a bit. And I guess to provide a more gentle approach to the topic than what might normally be done. I'll probably do something with this material on my YouTube channel. So if you really want to understand these concepts and equations in greater depth, you can either attend the conference in Poland, which would be fantastic. I'd love to see you there, or wait for that video to come out on my channel, or check out the material on PySDR.org. Dr. Marc Littman put a lot of the workshop on that website, so check that out. PySDR is just a wealth of information. So taking those equations, this is what the MVDR code looks like in Python. It's pretty simple, and most of it is actually just formatting the data for Python, as Python does not do matrix math well. In MATLAB, all of this would be like 2 lines of code. So we're just creating the steering vector S, and then creating the covariance matrix from the data, that X of t that we collected, and then we're inverting that covariance matrix, and then creating a new optimal set of beam weights. Again, you can find this code and some great explanation on Dr. Marc Littman's PySDR.org website. Okay, so let me try to do a live demo of this because live demos are always more fun, and I'll also post the code on the GitHub link shown here. But this is what my setup looks like. I have 2 log periodic antennas connected to Pluto, and these are just $10 antennas that I got from Amazon. And then I have 1 antenna connected to transmit, and this will be the signal that we track the direction of arrival of. And I'm showing low pass filters in this diagram, and those really should be connected, but I forgot them in my setup here. So, oh well, I mean, it'll work okay, but really it's best practice to put those low pass filters in, and you'll want to set that corner frequency just a bit above the R frequency that you're looking at. So for this setup, I'm at 2.1 gigahertz. So if you had like a 2.5 or 3 gigahertz low pass filter, that would be ideal. Just something so that the filter will significantly attenuate anything at 4.2 gigahertz or higher. But let's give this a try now. Let's see how it runs. Okay, so let's give this adaptive digital beamforming a try and see how it looks. So you can see here in Spider, this is the Python program that I have running, and this is posted at the GitHub link that I have. So you can try this out yourself if you want. Let me just hit run, and we'll observe this. So what we're seeing now are two traces looking at the power of this transmit signal here. In blue is just a conventional, I guess, kind of way that you might do this, basically looking at the power as you adjust the phase difference between RX1 and RX2 to change your scan angle. So that's in blue, and then in orange is the MVDR approach. So the MVDR, because we're adaptively nulling out the noise or whatever, provides a much sharper peak. So you can see that algorithm that I showed you earlier running. And as I move my transmit signal kind of back and forth, you can see that, I mean, both give you the peak where they should, at the direction of arrival as I move this to the left and to the right. But the MVDR approach gives you a much sharper peak. And so anyway, just a fun example if you want to play around with a little bit of understanding and using adaptive digital beamforming. Again, this script is available. Okay, let me talk now about a new feature on Pluto, and this is the TDD engine. This is actually pretty cool and allows you to do a lot of neat things. So in the last example, we did that with Python. So for this example, I'm going to do this with GNU Radio just to mix it up a little bit. So the plots and the presentation might look a little bit different, but it's all basically that Python module code that I pointed out at the beginning of this presentation. So here is 4 FMCW chirps. So these are frequency ramps that I am sending from Pluto's transmit directly into its receive port. So I'm getting buffers of received data, and we're just getting them at random times, just whenever the USB sends them to us. So you can see that there are 4 chirps in there, but their start and end time varies with each snapshot of data, just based on where the chirp was when we started to create a new receive buffer. But now we run the exact same code, but with Pluto's new TDD engine enabled, and this is what we get. So the start of each receive buffer now aligns with the start of each transmit buffer. And this is very useful for a number of applications. For me, I was mostly interested in using this with radar. For radar, we need to align our transmit and receive waveform before we perform a matched filter on the received data. And there's other applications too, like half duplex communication, where you want to control when you're transmitting and when you're receiving. So this new TDD engine allows you to do that. Okay, so if that sounds cool, then how do we do it? First, I guess what I should have called step 0 is to download the latest Pluto firmware. This only works with firmware Rev 0.39 and later. Okay, and then in step 1 is to set up the TDD attributes, and I'll show you what those look like on the next slide. Step 2 is to trigger the start of the TDD, and this can be done either as a GPIO input or as a software command. And then step 3 kind of happens automatically, and that is whenever you request a new buffer of received data, the TDD engine will align the transmit buffer to that start of the received buffer. And then step 4 is simply to read back that received data. So really the most important piece to this is setting up the TDD attributes. So let's take a look at that here. So this is what the TDD attributes and the corresponding timing of them looks like. So Pluto's TDD engine comprises a trigger signal and then 3 channels. The trigger signal that you see at the top there is just going to tell us when to begin our timing. And the 3 channels are simply called channel 0, channel 1, and channel 2. Channel 0 is a physical output pin. It's L10P on Pluto's 14-pin header. And you may or may not use channel 0. It's not generally necessary, but what it allows you to do is to output pulses in relation to the receive buffer. And this is useful in some situations, and I'll show you one of those in a couple of slides. Channel 1 is the timing for the receive buffer, and channel 2 is the timing for the transmit buffer. And for each of these buffers, we're going to send a software pulse that is going to have just a brief on duration. And we often may want to repeat that at certain intervals, and those intervals are what we call the frame length, and you can see those in this diagram here. And of course, all these timings and delays and the number of pulses, all this kind of stuff that we want, all this is configurable, and I'll show you how to do that next. So in the right-hand pane, you can see the Python code for how you set up all these attributes. There's really just a couple of rules to follow when you're doing this. First, the transmit cyclic buffer on Pluto must be set to true. The cyclic buffer just means whatever's in the transmit buffer is just going to repeat every single time. If you wanted to change the transmit buffer, you would have to send a command to destroy the transmit buffer and then reload a new transmit buffer. So for using the TDD engine, you have to create a new TDD object, and we call that object TDDN, and that object has a bunch of attributes that we can now set. The first thing you'll notice is before we start programming any of the attributes, we set TDD enabled to 0. It must be 0 or false to change the TDD attributes. Sync external attribute should just always be set to 1. Burst count is only used when outputting pulses to channel 0. Otherwise, just set burst count to 0. Channel 1 and channel 2 attributes control the timing of the receive and transmit buffers. I mostly just set all the delays to 0, and you can see that here. But there are cases where you might want to offset the receive and transmit buffers. And then when you finish making your changes to the attributes, just remember to enable the TDD object and then issue some kind of synchronization start signal. And here's what that GNU radio flow graph and corresponding Python block code looks like. You can find this code and example on my personal GitHub page at the link shown there. And this was the code that you saw running a couple slides ago where we had the transmit and receive buffers synchronized with the 4 FMCW chirps. And here's a picture of what those external pin inputs and outputs look like on Pluto. So if you wanted to trigger these buffers from an external signal, you would use that L12N pin that's highlighted with the purple arrow. And if you wanted to see some kind of pulsed output from the TDD engine, then you would set that up in the channel 0 attributes, and you would see that on the pin highlighted in green there. That's L10P. And there's just one more thing you got to do to access those pins on Pluto. You need to create this GPIO object, and that's what I'm showing here. And you can find out more about what's going on there at the wiki link shown there. Okay, and so why would you want to do this? Why would you want to mess with these GPIO inputs and outputs? Here's an example of using these GPIO pins with Pluto. It's something that we do with this phaser kit here. So this phaser kit we haven't really talked about, but here it is here. On the back of phaser is Pluto. And so we use Pluto in conjunction with these ADAR-1000 chips to do beamforming and radar. So, so on this phased array platform, this phaser board, what I want to do is when I get a new buffer of data, I send a GPIO pulse to the purple pin, and then I get a series of pulsed outputs on the green pin. I send those pulsed outputs from the green pin to the TX data input of a PLL, and that PLL is the ADF4159. And then I have programmed the ADF4159 so that every time it receives one of those pulsed inputs on the TX data pin, it's going to output one frequency ramp, one FMCW chirp. So this is a very clean way to do something called stretch LO processing, and this allows us to get a very high bandwidth chirp while only having to digitize a couple of megahertz of bandwidth with Pluto. And just in case anyone's curious, here's what doing that looks like on phaser. This is running, the Pluto TDD engine in that configuration that I just showed you. So each refresh of this plot is a new trigger pulse that has been sent to Pluto, and then I've programmed channel 0 of Pluto to output 128 pulses. Each pulse has a period of 500 microseconds. So each pulse then triggers on the ADF4159 a 500 megahertz frequency ramp. And that gets transmitted out of phaser and then received back by phaser and then into Pluto. And then those 128 ramps get processed into this radar range Doppler plot that you see here. So this is a plot of range on the y-axis and then Doppler or velocity on the x-axis there, so you can see targets moving forward and back corresponding to positive and negative velocity. So every refresh of the plot is a new trigger event and a new set of 128 bursts. But there's a lot of other things that you could do with the TDD engine. So I hope the TDD engine discussion was interesting to you. Okay, now onto a slightly sadder topic, and that is an issue that we've had with some Pluto devices and their ESD diodes. So I'm going to tell you how to detect that and then how to fix it. So we're currently on Rev C of Pluto, and Rev C is also called Rev D. I think they're actually both the same, or there is no Rev C. Anyway, yeah, Rev C and Rev D are the same. And for this Rev C, we added these RF protection ESD diodes at both receive ports and both transmit ports. And this was done in an abundance of caution to protect these RF pins. I don't think we've ever really seen any issues with people ESD zapping these pins. I mean, you would have to somehow zap the middle conductor without touching the grounding around it. I mean, I think it would be difficult to do. So this might be, I guess, a classic example of fixing something that wasn't broken. And the problem with adding these diodes in is that they're very small and they prove to be difficult for our manufacturer to assemble. And specifically, it was hard for them to get just the right amount of solder paste onto the pads. And so what sometimes would happen is that there'd be too much solder paste there, and the solder would bridge the pads across these RF diodes, and this would short that pin to ground. And this has been a surprisingly difficult thing for us to catch in our final testing of Pluto. And so some Pluto devices in the field are going to have these solder shorts across one or more of their transmit or receive ports. I'm pretty sure that future builds of this Rev C of Pluto are not going to have these ESD diodes installed. We're just going to skip it altogether. And those Plutos are still going to say Rev C on the back of them, but if you open them up, they just wouldn't have these four RF diodes that you see circled in red here. So it's always best just to do a quick and really a very simple test to see if you have an issue like this on your Pluto. And to do that test, you can use Python or MATLAB. But actually, what I recommend is a program called IIO Oscilloscope. IIO Oscilloscope should be part of your standard download whenever you install libiio or IO drivers or PyADI IIO or the MATLAB board support package. It is a separate download, but I recommend that everyone install it, installing IIO Oscilloscope. It's just a very handy debug tool, because if something is not working in IIO Oscilloscope, I promise you it is not going to work in Python or MATLAB or GNU Radio or whatever. So it's very useful if you're seeing something odd to debug it first in IIO Oscilloscope and make sure that everything is working properly there. And then once that is working, you'll know that your issue is specific to whatever binding you're using, MATLAB or Python or whatever. And then you can debug that further from within that program. So here are the settings that I used in IIO Oscilloscope, and I'm just creating a simple sine wave, and I'm looping that back to the receive port. And with these settings, if you see something like more than like a 1,000 peak ADC count, then you should be good. There shouldn't be any solder bridging on that transmit or receive port. But if you see something less than that, and in some cases it'll be very small, maybe a count of 100 or something, then you may have it. Then you have an issue. Of course, you won't know if it's on the transmit port or if it's on the receive port, but it's easy enough to just fix on both ports. And that's what I recommend you do if you see an issue. I would recommend just removing all four of those ESD diodes, and I'll show you how to do that next. So the best way to remove these ESD diodes is actually just to kind of scratch them off with your fingernail, just kind of knock that little black plastic diode off. And then with a soldering iron and some solder wick, just kind of soak up that excess solder and remove whatever's left of the diode. In that lower right image, you can see what the solder bridge looks like. So this was under one of the ESD diodes that I had. So I just wiped that solder away, and I redid my test and in IIO Oscilloscope, and I saw that everything looked good then. So I hope that this is helpful. Sorry about the trouble with the ESD diodes, but hopefully it's not too difficult for you to test your Pluto, and if you do see an issue, to quickly fix it. Okay, finally, our last topic here. I wanted to talk about a relatively new feature in the libio library, and we actually use this extensively in the Phaser project, and this is called context port forwarding. This applies to pretty much any IIO object, but I'm going to talk about it specifically regarding Pluto. A special thank you and a shout out to Mr. Marc Thoran for helping me understand this and for putting together a lot of the documentation and these slides for it. Okay, so here's a problem that, I don't know, you may or may not have, but it actually pops up in different ways, so it is interesting. So say you had 4 Pluto devices and say they were really far away. how would you connect them back to your computer so that you could control Pluto with Python or MATLAB or GNU Radio? There's a couple of options that you could do right now to do this. One option is you could just connect really long USB cables or really long Ethernet cables to each one individually and do like that. You can do it. It kind of becomes a mess though. So a new option now is to use this thing called context port forwarding. And if we did that, then we could connect these 4 Plutos to something like one Raspberry Pi or some other computing device, and then use context port forwarding to directly send that data from each of those 4 Plutos directly through, say, the Raspberry Pi over the internet, over the Ethernet into our computer. So everything we're doing, Pluto, all the programming, all the back and forth, it's all under this IAO driver environment. And there's a lot of terminology associated with IAO, but the one thing of interest for our conversation right now is this context. What is a context? A context is just a collection of IAO devices. And this context is connected to one computing device, like a Raspberry Pi, like an FPGA, or a microcontroller computer. Each context may contain 0 or more IAO device objects, but an IAO device object can only be associated to one context. So the phaser kit we saw earlier, that actually has 2 contexts here. So this phaser kit here, there's the Raspberry Pi that talks to the beamforming chips and synthesizers over the SPI bus, as well as this little I2C housekeeping ADC. And then the other context is the Pluto, which itself runs a small but complete Linux system. From the viewpoint of a program running on the Raspberry Pi, the stuff on the SPI and I2C bus are the local context because they are connected directly to the Pi. Pluto is connected via a USB cable and is accessible both through a USB backend and a network backend. So we can run Python on the Raspberry Pi and we can talk to everything just fine. I mean, all that works. But oftentimes we do want to talk to the phaser from an external computer. And the Pi has very limited processing power. It can't run MATLAB and certainly can't run a lot of other Windows applications. So during the initial development of the phaser code, we saw, the Raspberry Pi quickly became a bottleneck in what we wanted to do. And, other people wanted to use, fancy IDEs like Spider or PyCharm, and run things on a much more powerful laptop. And we couldn't run those on a Pi. We also knew that we'd need to support MATLAB and other development environments like VS Code and other languages. And so the solution we started with at first wasn't terrible, but also not very elegant. And the solution was we just connected to the Raspberry Pi via Ethernet, and then we separately connected to Pluto over just a very long USB cable. So Pluto was no longer connected to the Raspberry Pi, and we just had 2 cables going to the laptop. And this worked, but it just wasn't super elegant. But with context port forwarding, we can run just one Ethernet cable from the Raspberry Pi and yet still retain Pluto's unique context. And this was a feature added in libiao version 0.24. And it works with any context, a local, USB, serial, whatever. And the way it works is we first start a little service on the Raspberry Pi called IIOD. And this will forward all the locally connected devices over a network backend. Then to access those devices, we just use the Raspberry Pi IP address, which on the phaser board we've set to phaser.local. And then we add the port number in that we assigned when we started that IOD service for that Pluto. Here I show the port number as 50901. That's just what Marc Thorin chose for this example. You should choose some other port number or a random port number. There's an interesting reason why you should stay away from common sequences and numbers, and you can read about that if you're curious at the link in the lower left-hand corner. Okay, so how do you do this? How do you start up the server? How do you set this up? On the Raspberry Pi, running the Kuiper operating system that we normally do with these systems, you just enter in this command, and you can see it at the top there, IIOD -P, and then the port number that you want to assign, then -U, and then the IP address of the IAO context that you want to be forwarded. And then on your computer, if you open up IAO oscilloscope and hit refresh and scan for all the IAO contexts, it will find that context that you just forwarded over the Ethernet cable, and it will report back to you that there is a Pluto device, and now that Pluto device has a context of phaser.local:50901. But you don't have to type that command into the Raspberry Pi each time you boot up. You can do it automatically at startup. And in these terminal commands, if you can kind of see those commands there, if you kind of zoom in these terminal commands, you can see the links to some of the scripts that Marc Thorin has put together to do that automatically each time your Raspberry Pi starts up. And of course, you could do that with multiple Plutos together. Here's 4 Plutos. Each has a different IP address and each has a different port that we're forwarding into. So the first step is to give the Plutos unique IP addresses. This is very easy. Just edit a text file in the Plutos mass storage device. The next step is to run 4 instances of the IIoD service, telling it which IP address to forward to which port. to which port. And now each Pluto can be uniquely accessed by appending its port number to the Raspberry Pi's IP address or host name. So now all these Plutos can be interacted with from a long distance away from your computer, and you can be running MATLAB or GNU Radio or Python and again, it doesn't have to be Plutos or devices like that. You can also do this with serial backend devices. Really, any IAO device, whatever context it has, you can forward it using this service here. So context forwarding provides another way to connect these boards, whether to extend the reach beyond the maximum length of a USB cable, or to aggregate multiple devices, or allow access from a host that has maybe a limited or no free ports. So I hope that was interesting. Hope that was helpful. We talked, just to review here, we talked a little bit about the basics of Pluto, including how to enable that second transmit and the second receive channel. And then we did what I hope was a cool adaptive beamforming example with those 2 channels. Then I explained how to set up the new TDD engine in Pluto firmware Rev 0.39 and showed how you could use this to control the timing between the transmit and receive buffers. And then I warned you about a small ESD issue that may or may not be affecting your Pluto. So everybody go home and test that out. And if it's a problem, now you know how to fix it. And finally, we concluded with the new context port forwarding built into IAO Rev 0.24 and later. So I hope that was interesting. And if there's time, I'd love to answer any questions that you may have.
So, yeah, thank you for this very insightful contribution. Since I have a ADALM-PLUTO at home as well, I will return tomorrow afternoon and do some experiments. Who in the audience has an ADALM-PLUTO at home? Yeah, that's good, that's good. So you got some valuable input also. Do you have some questions? Okay.
Hi, Paul Boven here. Thank you for your very interesting contribution. I am currently playing around with another very nice analog product, the ADL-5961. And what you told me today sort of solves a problem which I've been having, which is how do I sync the sweep to what I get? But in your slides, because I'm basically doing the same thing, I'm doing a sweep, I want the TX out, I want the RX in, I want it to be combined. But in the flowchart you were showing, it basically comes in as complex samples. Is there a way in GNU Radio to synchronize this up with your start pulse so that you basically end up with vectors that contain one complete sweep, so that, for instance, you could start averaging over sweeps and things like that?
And in GNU Radio, you want to do that?
Yes, please.
Yeah, so yeah, GNU Radio is fantastic, but I am not an expert in it. I don't so the way that I would do it is actually in Python and using that Python block in GNU Radio, because I think there is a way with tags and stuff that you can tag a message stream and allow it to synchronize, but I don't know how to do that. And you would have to do something where once you get a receive block, you have to hold the flow graph of other data in GNU Radio until you finish your processing and process that in a batch. So I think the answer is yes, you can do that, but it needs to be somebody smarter at GNU Radio that needs to take a look at it. Yeah.
Okay, thank you.
More questions? Mario?
When you have a protective ESD diode, and you suggest scraping it off with a finger. Isn't that somewhat, I should say, dangerous in an ESD kind of way?
Yeah, that's a good point. Yeah, I mean, I usually do an ESD strap or something like that. You see one on my bench. That's always best practice. I can say, I mean, I've done this hack on probably 30 or 40 Plutos, and it's always worked great. So I don't know. They're good. I'm sure there's a better way to do it. Maybe there's an official analog devices technique to do it, but I don't know. It seems to work.
More questions? Okay, question from the chat.
Yes, one comment, I guess. But please be aware that the GPIOs are 1.8 volt and not tolerant to 3.3 volt. I hope this was for this talk. I'm not sure.
Yeah, that's a great point. Yeah, thanks for bringing that up, whoever said that.
Yeah, and one question. Will the TDD engine allow vectorial network analysis by connecting a DOT between a TX output and an RX input, sweeping the frequency and measuring receiving amplitude and phase?
Okay, yeah, I mean, we have had people set up Pluto as a kind of VNA. I don't know that you need the TDD engine for that, but maybe the question is, using those FMCW chirps that I was using, can you, now that you're synchronized, the frequency on the transmit as you're sweeping that chirp and the frequency on receive as you're synchronizing that chirp, maybe you could do a much faster kind of a VNA implementation. That's interesting. I mean, that could be that could be worth a try. Yeah, that could work.
Okay, cool. More questions? No more questions? Okay, so then, thank you very much for coming in. Thank you for sharing your insights and thoughts and projects. And I think that's a good starting point for your own tests and experiments, and also for my future experiments. So, excellent. Thank you very much.